Okay, guys, so we finished the class, the last little video. We were talking about sampling distributions. We have a sampling distribution, a beautiful symmetric normal curve. And we said, if n is greater or equal to, say, 50, then we have a normal distribution. And the mean of this normal distribution is basically the population mean. So the expected value of x bar is just the population mean. So we can think that the population mean is in the middle, and the standard error is sigma over root n, which actually we don't normally know the population standard deviation, so we have to use the sample. And that's just telling us the example I gave with the lime and the calories. The bigger the sample we have, the closer it is to the overall population mean. If we have 20,000 students at Mississippi State and we're measuring their average calorie consumption, if we sample 10,000 of those students, it's probably going to be pretty close to the population mean. So as the sample size gets bigger, we kind of get the variance, the standard deviation gets smaller. Now all a confidence interval is we just literally flip this guy around. So we actually put, this is the sampling distribution. It has all of these x bars in it. It's just basically this distribution of all the hypothetical sample means. Now, obviously, we can't take lots and lots of samples of 50 or whatever. That defeats the point of sampling. But we take one sample, and we just imagine it's flipped around, and then we kind of make inference on the population mean. And then we'll say something like, for example, we're 95% confident. Now, the non-technical ways will say we're 95% confident that the true mean is in this area of the curve. But in fact, the better way of saying it, the more statistical way, is like in the long run, the true mean, mu, will be in the confidence interval. (95 out of 100 times). So it's really just that's kind of just if we completely take a sample, take another sample, 95 times out of 100, the true mean will be in our confidence interval. Now let's define our confidence interval a little bit more closely. Another beautifully drawn normal distribution. So we have the x bar in the center. Now this is normal. And remember, if we have a normal distribution with a mean of 0, this is say a mean of 0 and standard deviation of 1, then the scores for certain probabilities are called the z-scores. So we'd have a z-score for 95% of the distribution. We'd have a d-score for 90% of the distribution. These are just standard normal scores. But, in fact, our standard error is sigma over root n. So we need to multiply our z-score by the standard error. Now imagine that we have 100% 1 minus alpha confidence interval. So 95%, my alpha is 0.05. 99%, my alpha equals 0.01. Now, as our percentage confidence gets bigger and my alpha gets smaller, my confidence interval gets wider. If I need to be more confident, I need to cover a wider area. Now this is, so imagine we have 100% 1 minus alpha. This is a probability. So the area of a probability is always going to be 1. So I have 1 minus alpha. And then the remainder I just split in 2. So the remainder is alpha, and this is alpha over 2. And this is alpha over 2. So this we add, to get to here, we have to add, because it's a standard normal, we get the z-score, z alpha over 2. But because we don't have a standard error of 1, we have a standard error of sigma over root n. We need to multiply by sigma over root n. And we do the same for the subtraction. So we can actually define our confidence interval more formally now as x bar plus or minus c alpha over 2 sigma over root n. And, you know, we can also say, if we use the sample value, this is going to be s over root n. Okay, now let's just go back to R for a minute before we do the calculation. So we have some data on Black Friday shopping. And this is just a little example from one of the stats books I've taught from. And it's basically Black Friday. All we're doing here is we're reading in a spreadsheet. And we're using this library called OpenXLSX. That just allows us to read spreadsheets. So we load the library in. And all this is saying, if not required, this just means if we don't already have this, then we install it, and library tell us to open it so we can use its functions. And then we're using a function called read.xlxx. And we can actually see what's in this. Well, we've got some information. We've got the age of the consumer. We've got something, maybe how many years they've been Black Friday shopping, the time they went shopping. But for the moment, we're only interested in the number of hours. We want to make inference on the number of hours they've been shopping. And what we want is we want a 95% confidence interval. So if you recall, we're doing x bar plus or minus z alpha over 2 sigma over root n. Now, let me just go back to this. So if we've got this guy here is called the margin of error. And this is like half the width of the confidence interval. So this is like, we've got our x bar, and I'm not going to draw the distribution. This guy is half the width of the confidence interval. And if we subtract it, that's the other half of the confidence interval. So again, this class, we're not going to get into the calculations, but you just need to know how we just need to know, you know, the kind of how confidence intervals work. Okay, so let's go back and let's begin to work with this data. So we set our alpha, which is alpha 0.05 for a 95% confidence interval. We set the length, which is, find my n, which is 38. There were actually 38 people in my sample. It's a very small sample. We calculate the mean, and we calculate the standard deviation. And as I said, we generally don't know the population standard deviation, so we have to estimate using the standard deviation from the sample. So let's just see, what are these values? We have my x bar, and we have my 6.07, my standard deviation 3.33. Now the norm margin of error, now we used the d-norm function before. Here we're going to use the q-norm function. And basically we're going to say that the q-norm function, this is, I'm not going to actually ask you for this in any of the homeworks. We're just going to use the standard functions. But if you go back, let me just kind of go back to my sheet. and this one's for what kind of all you engineers out there. When we in our little statistics books that we use in the business school, and because most of the class have taken business stats too, I've used this to be consistent. When we do a z-score, we call this z alpha and this z minus alpha. But in fact, if we were to think starting at 0 and going all the way to 1, and this is like the cumulative probability, then this would actually be z alpha and this would be z1 minus alpha. Now our business stats textbooks worked like this, and probably most more mathematical textbooks would work like that. So just if you want a z alpha, you have to actually call it z1 minus alpha, just to make things more complicated for you. So we have the Q norm basically is the z-score function. It basically means that kind of the quintile, and then we multiply it by the standard deviation divided by the square root of n. So exactly in the formula I just gave you. And the confidence interval is just the mean minus the margin of error and the mean plus the margin of error. So my confidence interval is like that. So we can say, you know, if we're using the non-mathematical way, we're 95% confident that the true mean score is between these two values. And in business, we would tend to use this if we're, you know, we can convert our mean shopping hours into some sort of profit, then we would actually have, you know, some sort of bounds for our profit and loss calculation. So that's just a very simple confidence interval. Now we're just going to do the same, but we're going to do it with the t. Okay, so next we'll deal with a situation where we have n is less than 50. What do we do then? Because the normal distribution relies on the fact that n is greater. Sorry, the central limit theorem relies on largest n. Now, if n is less than 50 and our underlying data are normal, then we use the t distribution. And interestingly, this was actually invented by somebody called William Seeley Gossett, who was a brewer at Guinness and wanted inference on, you know, maybe they made a small number of barrels of different types of beers, so needed these small sample statistics. So the underlying data are normal, and we have a smaller sample size. We can use a t distribution. But also, if n is greater or equal to 50, then the t distribution kind of trends to the normal. So we can also use the t distribution for large sample sizes. And what, in fact, most statisticians, and I put a bit more detail about this in the notes, is that most statisticians actually would prefer the t distribution because it doesn't like estimate the sample standard deviation for the population standard deviation. It just relies on the sample standard deviation. They prefer it to the z distribution. So the nice thing about that is you can pretty much ignore the z-test in R. And R has lots of functions for the t-test and t-distributions. Now, if this is a normal distribution, an interesting thing about the t-distribution is it gets kind of wider for smaller n's, which makes sense. You're less sure for smaller n's, so you have a wider distribution. This is the normal. And imagine that we have a t distribution. And we could say maybe that this is t with n equals 10. And we'd also say the degrees of freedom is 9. And that we don't want to go into too much about it, except that it's n minus 1. But essentially, if you calculate a statistic, every time you have a data item, you have a degree of freedom. You calculate a statistic like a mean, suddenly you have one less degree of freedom, because we still need to keep the mean. So we lose a degree of freedom. So, but for the moment, just for calculating t, you need degrees of freedom. And as n gets smaller, this distribution kind of becomes narrower. So it becomes wider. So n equals 5. Degree of freedom here equals 4. Okay, so let's kind of clear that. And the t-test is pretty much exactly the same as the z-test, but we're just going to use a t rather than a z. With t, with the t statistic. And this is x bar plus or minus. So it works in exact, I'm not going to show you the pictures again, it's exactly the same, plus or minus t alpha over 2. But this time we're a sampling distribution, so we don't have to kind of almost assume that the sigma is s, it's already s. And I'll just give you a little bit of a visualization. So we have the x bar in the middle, then we have plus t alpha over 2 s over root n, which is our margin of error, and then we have our minus t alpha over 2 s all over root n. And sometimes when I do it, I'll actually write the degrees of freedom in the t statistic, so it will be with n minus 1 degrees of freedom, n minus 1 degrees of freedom, n minus 1 degrees of freedom. Now, if you recall, in your business stats, when you were calculating this, you just looked at the distribution at the back of your textbook. That there would be kind of, you'd have your different alphas, and then you'd have on the columns, and then you'd have your degrees of freedom down here, and then you get the t statistic. But here we can just let R do this for us. So let's go and let's have a look at our second examples. And this is called screening. So let's just have a look at this data. And this data is basically, it's getting a lot of stock screeners. Now what a stock screener does is it basically gives you a set of rules for investing in stocks. So I want all stocks with market capitalization of over $1 billion and less than, say, a certain amount of debt to equity ratio and less than a certain amount of price to earnings ratio. So it's just, even if you don't understand the finance, it's just ways of picking stocks. And basically we're looking at a load of different stock screeners, in fact 13 different stock screeners, and calculating the average return. So again, we don't really want any of this other junk, so we just want the return. Now, we calculate the n, the mean, and the standard deviation. Now this time we want a 90% confidence interval. Now, for a 90% confidence interval, I should actually have wrote that in the notes. We're going to be 100% 1 minus alpha is going to be 0.1. So we're going to have the margin of error is the same as before, but instead of Q norm, we use QT, and you see we actually pass it the degrees of freedom, which is n minus 1. Exactly the same as normal, but we use QT instead of Q norm, and we're passing it n minus 1. And the confidence interval is you just subtract the margin of error and you add the margin of error. This is my confidence interval, and 7 and 14. So even for the moment, I'm going to just allow you to use the t-test function. This is all very useful stuff to learn, because you may actually utilize these distribution functions, and you're certainly going to have to use the mean, standard deviation, and length function. So it's all like a learning experience. So having said that, we've got our confidence interval. Now we notice it's pretty wide, which is not surprising because we have a very small sample size. So our standard, the divide by square root over n isn't having a huge effect. But let's just see. Now, to do a confidence interval, we actually use the t.test function runs hypothesis tests and it runs confidence intervals. So we run t-test and we base it on return and we just put the confidence level. Now this time it just asks you for the 1 minus alpha. So our confidence level is 0.9. And the res screen actually gives us lots of information. Because the actual test we're not using, so we'll ignore that at the moment. But we actually get the confidence interval, which is exactly the same as we calculated manually. So we can be like 90% sure, or more technically in the long run, 90 times out of 100, that the true mean, given this like large population of possible screeners, is between 7 and 14. And again, we can actually extract the confidence interval. This little $sign I'm using, if you've got a data frame and you want to pick one particular column or one particular item, the $sign is just saying, hey, let's go down to the next level.